Figure 4 shows a sketch of a Ferris wheel. The height above the ground, h meters, of a passenger on the Ferris wheel t seconds after the wheel starts turning is modelled by the equation h is equal to the modulus of a sine bt plus alpha, where a, b and alpha are constants. Figure 5 shows a sketch of the graph of h against t for one revolution of the wheel. Given that the maximum height of the passenger above the ground is 50 meters, so that basically means that the y-coordinate or h-coordinate for this point here is 50. So the x or t coordinate is unknown, but the y-coordinate is 50. We're then told that the passenger is 1 meter above the ground when the wheel starts turning, so that tells us that this coordinate here is 0, 1. The height is 1 to begin with. The wheel takes 720 seconds to complete one revolution. We're also told that what we have here is one revolution, so that means that this time here would be 720 seconds. Part A is asking us to find a complete equation for the model, giving the exact value of A, the exact value of B, and the value of alpha to 3 sig figs. So we want to work out A, B, and alpha. So what we have here is a transformation of a sine graph. The A, B, and the alpha corresponds to different transformations. So let's run through those. A represents some kind of shift towards the left or right. And actually looking at our graph, it seems to be the case that the graph has been shifted towards the left somewhat. Normally a sine graph will cross at the origin. If we continue this curve, we see the sine graph will cross somewhere just to the left of the origin when h is 0, so somewhere over here. So it seems to be shifted towards the left. Then we have B. This is some kind of stretch. It's a horizontal stretch. A is a vertical stretch, and the modulus function will reflect everything that we have beneath the time axis to be above. And we can see that happening here. Normally the sine curve will continue to go down, but what's beneath the time axis here has been reflected above. So we can work out A, B, and alpha by considering the points that we have here. Let's start with the 50. So normally for a sine curve, the maximum height of that curve is 1. Here it is 50. So there has been a stretch of scale factor 50 parallel to the y-axis or the h-axis. In our equation that we have over here, A is what corresponds to the vertical stretch. So in that case, A would be equal to 50. If A is 50, the sine graph has been stretched by scale factor 50 parallel to the y-axis. We can then look at the 720. So normally for a sine graph, this would be 360, this would be 180. We are working in degrees as we see over here. And if we were to do the modulus of this curve over here, it would look something like, I'll put it in blue, it would look something like this. So we are seeing this portion of the altered sine graph, which corresponds to, on this graph over here, starting from about there, going up and then back down to here and then up a little bit. Whatever we've missed out over here, we have over there. So in other words, on a regular sine graph, what we have here corresponds to 180 degrees. Here, that's equal to 720 degrees. So we have half of an oscillation of a sine graph here. That normally corresponds to 180 degrees. Here it's 720. So that means when going from this graph to this, the x-axis or the time axis has been stretched by a scale factor of 4. Because 4 times 180 is 720. Stretch this horizontally by a factor of 4, and we end up with what we see here. To stretch something horizontally by a scale factor of 4, let's say we have f of x is sine x, we'd have to do f of a quarter of x. So that would turn this into sine of a quarter x. That will be a stretch scale factor 4 parallel to the x-axis. So it's what's next to the x that causes that stretch parallel to the x-axis. That's the b in this case. So to achieve that same stretch, b should also be equal to a quarter. So b is a quarter, and now we can go on to alpha. So our equation right now is h is equal to the modulus of a, which is 50, times sine of b, which is a quarter, times t plus alpha, which we don't know. The last point that we have yet to consider is this one here, the 0, 1. We've used the 50, we've used the 720. The 0, 1 we can just simply input into this to work out what alpha is. So when t is 0, h is 1, so 1 is equal to the modulus of 50 sine of, so a quarter of t would be a quarter of 0. That would be 0, so we're just left with sine of alpha. Sine alpha, we can then take the 50 out. We get modulus of sine alpha, and that would then become sine alpha is plus or minus 1 over 50. If you remember, if you have modulus of x is equal to 5, that's the same thing as saying x is equal to plus or minus 5. If you put plus or minus 5 into this modulus symbol, it gets rid of the sign and just makes it positive. So both of these will work in replacing x. And if we do inverse sine of 1 over 50, we get alpha is equal to 1.15 degrees. If we do inverse sine of minus 1 over 50, we get minus 1.15. So basically we get plus or minus 1.15. So which one is it going to be? Could it be either one, or is it just going to be one of them? Well, if we think about the graph that we have here, and where alpha is inside this function here, alpha represents a horizontal translation. If alpha is positive, that corresponds to a shift towards the left. If alpha is negative, that corresponds to a shift towards the right. As we discussed earlier, this graph has been shifted slightly towards the left, so therefore alpha should be positive, so we are considering alpha is equal to 1.15. Our final answer for h would then be 50, modulus of 50 sine a quarter t plus the alpha, which is now 1.15 degrees. And for part B, explain why an equation of the form of this, so same equation as what we had before, but with a plus d on the end, where d is a positive constant, would be a more appropriate model. Okay, so what is that plus d doing? So this was our original equation, we have the plus d on the end, that will be a vertical translation, everything would move up d units, it will be a translation of vector 0, d. So what does that look like? So our original graph, before this shift up of d units, looks something like this. I'm just resketching what we had above. That's all we had to begin with. If we move that up d places, it will then look something like this, where this distance above the ground is d. Why is that better? Well, if we think about what this model represents, on the y-axis is height, it's the height of the passenger above the ground. In the model that we have over here, we see that every cycle the passenger touches the ground. Because their height above the ground would be 0, that means they're touching the ground. That doesn't make sense for a Ferris wheel. For a Ferris wheel, the person is always elevated above the ground. There will always be some minimum distance above the ground, and this equation here includes that minimum distance above the ground d. So our answer, we can say, in the old model, the passenger touches the ground every cycle. In the new model, the passenger has a minimum height of d above the ground.